Welcome to Section 8.1, Part 2. This is the 60-second session of the CISSP exam prep series. This part continues our tour of secure design principles. In this session, we'll cover how systems should behave when things go wrong and why simpler is safer. We'll answer several questions. What does it mean to fail securely? How do you handle errors and bad input gracefully? What is the difference between fail-safe and fail-secure? How do those terms flip between the physical and digital worlds? Why does simplicity make a system easier to protect? And how does explainable AI extend that idea? Why does this matter beyond the exam? Because failure is not a maybe, it is a when. Imagine a badge reader at a data center loses power during a storm. Whether those doors spring open or slam shut is a design decision someone made long ago. On the job, you are often the person asked to make that call, and getting it wrong can trap people or expose assets. Thinking clearly about failure and simplicity is daily engineering, not theory. So what does it mean to fail securely? It means a system is designed ahead of time to land in a safe, predictable state when something breaks. Failure can come from countless causes, but what matters is how the system responds. A program only fails securely because a developer planned for it. Think of an aircraft that is engineered so that even a hydraulic loss still leaves the pilot able to land. The safe outcome is not luck. It was built in. How do you handle errors and bad input gracefully? You start with error handling, sometimes called exception handling. That is code written to anticipate problems and deal with them before they crash the program. Many languages offer a try-catch structure. You place risky code in the try branch and recovery code in the catch branch, so an error is caught instead of fatal. Then you guard the front door with input validation. You check user input for length, filter out known bad patterns, and neutralize dangerous characters. Picture a bouncer who inspects every guest before the door, rather than chasing troublemakers once they are already inside. What is the difference between fail-safe and fail-secure? Both describe a complete failure, but they protect different things. Before that, note the gentler option, fail-soft. To fail soft is to let a system keep running after one component dies, like a multitasking computer where one crashed app does not take down the others. When full failure is unavoidable, you must choose a priority. Fail-safe protects people first. A fail-safe door unlocks in an emergency so everyone can escape. Fail-secure protects assets first. A fail-secure vault door locks itself down when an alarm trips, even if that inconveniences whoever is nearby. One saves lives, the other saves valuables. How do those terms flip between the physical and digital worlds? Context changes their meaning, so pin down which world you are in. In the physical world, a fail-open response leans toward availability and goes by the name fail-safe, while a fail-closed response leans toward protection and goes by the name fail-secure. In the digital world, the focus shifts to the core triad. Fail-open keeps a connection flowing to protect availability, the way a firewall might pass traffic unfiltered if it crashes. Fail-closed cuts the connection to protect confidentiality and integrity, blocking all traffic instead. When an operating system hits a memory isolation violation and halts into a stop error, that is failing closed on purpose. Always ask first, physical or digital, before you translate the term. Why does simplicity make a system easier to protect? Because complexity is where security goes to hide and break. This is the keep it simple and small principle. More lines of code mean more to test. More parts mean more places to fail. More features mean a larger attack surface. Related ideas reinforce it. Do not repeat yourself, so a fix lands in one place. Build only what you actually need right now, not every feature you can imagine. Use the least powerful tool that solves the problem. Think of a Swiss Army knife with 40 blades. Half of them just add ways to cut yourself. A lean design is easier to secure, troubleshoot, and verify. How does explainable AI extend that idea? It carries simplicity into the world of machine learning. A black box model that no human can interpret is a security risk, because hidden logic can conceal bias, flaws, or tampering. Explainable AI adds transparency, letting you trace how a given input produced a given output. Interpretable models go further, staying understandable by design. Guidance like the NIST AI risk management framework stresses systems that are reliable, accountable, and transparent. Think of a chef who lists every ingredient on the menu so no hidden allergens slips through. Visibility is what lets you actually assess the risk. So let's bring it together. Failing securely means designing the safe landing before the crash, using error handling and input validation to stay in control. Fail-safe protects people, fail-secure protects assets, and those labels flip meaning between the physical and digital worlds. So always check context. Simplicity shrinks the attack surface and makes everything easier to secure and verify. An explainable AI pushes that same transparency into modern models, designed for the bad day and keep it lean. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.